Hi, this is Michael Kogan. I'm doing problem one on test three for physics two. So we'll just hop right in there. For A and B, most of the constants stay same, so I'll just label it up top. When we're dealing with Q1, which will be an electron, that equals negative 1.6 times 10 to the negative 19 coulombs at distance 1 of 1.00 times 10 to the negative 10 coulombs or meters. My bad. Sorry. Uh, and Q2, which will be our lead nucleus or lead atom in general, it will have a positive charge of 1.31 times 10 to the negative 17. And the final position that we're looking at is 5 times 10 to negative 10. So let me explain the full problem real fast. So for this problem, we have an electron at this distance of d1 from a nucleus with that charge of q2 at here, and we want to know how much work it takes to move the electron from here to here at d2. To do this, we'll use this equation. Very easy setup. It is k times q1 times q2 times 1 over Ri, which is the initial distance, minus 1 over Rf, the final distance. And that will equal work done on the particle. And since this is negative and this is positive, you got to remember that the field lines are attracting. So proton points away, electron wants to go the opposite way of the arrow. So it'll be pointing this way. So we'll have positive work done. That's just one way that we can make sure and dummy check when we get our final answer. So we'll want to plug in our numbers first, right? So remember, k is 8.99 times 10 to the ninth power times negative 1.6 times 10 to the negative 19. That negative sign doesn't really matter, but it just helps remind me what we're dealing with. Times 1.31 times 10 to the negative 17 times 1 over 1 times 10 to the negative 10 minus 1 over 5 times 10 to the negative 10. Okay, so we'll plug in all those values into our calculator. Then we will get the answer of 1.5 times 10 to the negative 16 joules. And we can check that that is correct. All right, so that's problem A. Problem B is very similar. It wants to know the kinetic energy when it's at a distance of 8 times 10 to the negative 12 meters. So it'll be closer this time. So if you release the electron from point A, from the position A, that will what will be its kinetic energy when it's at distance 8 times 10 to negative 12. Okay, so we'll take it as position A is D1. So all we're changing is D2, the final destination. All right, so we'll set up the exact same equation, right? Same thing, K times Q1 times Q2. Because remember, work and kinetic energy are heavily related. They're just inverse of each other. So as it gets closer, it'll have more kinetic energy as negative work is being done to bring it there. So we'll start off with 1 over R1 minus 1 over RF. Let's remember RF now is equal to 8 times 10 to negative 12 meters. Okay. Oh, I'm so sorry. I didn't write down meters or coulombs on this one. But okay. Now that we have that, let's plug in our values. 8.99 times 10 to the ninth times 1.6 times 10 to the negative 19 coulombs times 1.31. Sorry, I'll pause a lot randomly. I have already recorded this video, but apparently I muted myself, so I'm just making sure I don't make that same mistake again. And then we'll multiply that against 1 over Ri, which is 1 times 10 to the negative 10 minus 1 over 8 times 10 to the negative 12. Okay, so then we'll replug in our numbers. Luckily, since this one's pretty much the same problem, we can just plug in the new values. And then we will get negative 2.17 times 10 to the negative 15 joules of work done. And remember, work is just the inverse of kinetic energy. So we can just take the times that by -1 to get the inverse, and then we'll just do work times -1 equals K, and that will be 2.16. Well, sorry, I forgot. We need to make sure to round off our numbers. 2.2 times 10 to the negative 15. And that will be in joules still. Same value, just different metrics. Sorry. I have this bouncing on a Windex bottle right now, so it may move a little bit. Okay, so then we'll move on to the next question. In a nuclear physics experiment, a proton mass 1.67 times 10 to the negative 27 kilograms, charge positive E, is fired directly at a target nucleus of unknown charge. You can treat both objects as point charges and assume that the nucleus remains at rest. When it's far from its target, the proton has speed 2.5 times 10 to the 6 meters per second. The proton comes momentarily to rest at distance 5.9 times, or 29 times 10 to the negative 13 from the center of the target nucleus and flies back in the direction from which it came. What is the electric potential of the proton nucleus when they are 5.29 times 10 to the negative 13? Okay, so that may seem like a lot, but let's just start off with the basics. Write down our values. So it looks like we'll be using these same values for D as well. So I'll write down C and D. And I'll write down mass of P equals 1.67 times 10 to the negative 27 kg. QP equals 1.6 times 10 to the negative 19 coulombs. And is fired directly at a target nucleus of unknown charge. So we don't know charge of Qn equals question mark. Target nucleus unknown charge. You can treat both objects as point charges, assuming the nucleus remains at rest. When it's far from its target, the proton has speed 2.5 times 10 to the 6. So its velocity of P equals 2.5 times 10 to the 6 meters per second. And then it comes, I'll put down dr for distance when it's at rest. Is 5.29 times 10 to the negative 13. So let's see if there's any shortcuts, right? Because we can look at this problem. We'll know, okay, we know how the equation for work done on an object, right? And with that, we also know the speed of this object and the mass, which means that we can find the kinetic energy. So we know how many joules is in the system right now. And if we assume that nothing's being added, right, as these two approach, right? And then it comes at rest here. So we can assume at this point, all the kinetic energy it had here is turned into work. So that'll be potential energy, right? Since it's at rest. So, in reality, for this one, all we have to do is just get the kinetic energy of the object. It's pretty simple. So, okay, I'll show you. C will be to find U, which is potential energy. We need K, which is kinetic energy. So I'll write down Ke just for simplicity, so we don't get confused here. And we'll use Ke equals mass times velocity squared divided by 2. Right? So then let's remember all of our values. 1.67 times 10 to the negative 27 times its speed, 2.5 times 10 to the 6 squared, and divided by 2. So we just plug that into our calculator. 1.67 times 10 to the negative 27. Sorry, forgot to put a negative there. Times, and we'll put this in parentheses, times 2.5 times 10 to the 6th. That's squared in general. And then divided by 2. Let's make sure all of our values are correct before we click enter. Okay, we have 5.22 times 10 to the negative 5. So that will equal 5.22 times 10 to the negative, not 5, sorry, negative 15 joules. Okay. And when we look at our answer that the book gives us, that is correct. So it's very important for you to remember that Ke and U are related. So I'll put that squiggly line just to show that they're related, but they're just the inverse of each other, right? And not like fractionally. I mean, just times negative 1. They equal each other times negative 1. Okay, so just imagine it as like 2 bars being filled. As you empty one out, another one gets more full, vice versa, right? That's the analogy I always like to think of. Okay, so then for D, what is the charge of the target nucleus? Okay, so this may seem a little complicated or a little confusing given that you haven't had to solve for this. But let's recall. Here, I'll write down first so that we can all remember to find charge N of the nucleus. We'll have to use the equation. Hold on, let me make sure. Give me 1 second here. We can use our normal equation of U equals K times Q1, Q2 divided by R, the distance between two charges. And if you guys haven't noticed, we already have U, right? We're given distance at where this U is valid. And we're given one of these variables, and we know what K is. That's a constant. So that means all we have to do is take UR Q1, and that'll be our nucleus charge, times K equals Q2. Right? So then we can do plug in our numbers, times 10 to the negative 15 times 5.29 times 10 to the negative 13 divided by 8.99 times 10 to the ninth because of the K value, and then Q1, which is the charge of the proton, times 1.6 times 10 to the negative 19. And that will get us our value. So now we just have to plug that into our formula, or plug that into our calculator. 10 to the negative 15 times 5.29 times 10 to the negative 13 divided by 8.99 times 10 to the ninth times 1.6 times 10 to the negative 19. Make sure. Okay. So then our value that we get for the charge of the nucleus is 1.92 times 10 to the negative 18 coulombs. If I'm not mistaken, I believe that should actually be impossible, since it's a nucleus. Sorry, but I'm not smart enough for that yet, and I don't get paid to think that much. Okay, but we can cross-check that. That's correct. So we can see that we can solve for a lot more than we thought we could originally. Okay, for part E. E through, let me see how many times we use these variables. Just to F. Should be easy. Okay, Mike's still not muted. That's great. Good to know. Okay, so I'll just read out the problem. 2-point charges are at fixed positions on the y-axis. Q1 equals positive E at y equals 0, and Q2 equals negative E at y equals A. Find the work you must do to bring a third charge, Q3, equals negative E from infinity to being at rest at y equals 2A. All right, give me 1 second. Sorry about that. Just had to check on my dog real fast. Okay. Back to our problems for part E. It's asking for 2-point charges are at fixed points on the y-axis. Q1 equals positive E at y equals 0, and Qt equals negative E at ya. So let's write that down real fast. Okay, so first one, these are both on the y-axis. Q1 equals positive E, y equals 0, Q2 equals negative E at y equals A. Find the work you must do to bring a third charge, Q3, equals negative E, from infinity to being at rest at y equals negative 2A. Negative 2. Okay, so this may seem very complicated. I know infinity is always a scary thing, but let's remember that we can always just sum up these distances. So, how I want you to do this is to take the formula to find work, use we'll just use the extended form Q naught. So that's the charge that we're bringing in. Uh, so that's the charge that we're bringing in. So that will be negative E. Negative E divided by obviously 4 pi in the permutation constant times e squared divided by negative 2a. Um, this one is the distance between Q1 and the distance from that to Q naught, negative e. Since Q1 is at 0, that'll be just negative 2a. And squared, I'm so sorry. I don't know why I'm making this error. Let's just make that one for now. Because it's multiplying each other on top. So this is, as we've seen before with the Q1, Q2 right on top. So that's why we get e squared. And then that will be, the next one will be plus e squared divided by 3a. Since it's at, here, I'll write this out for us. Here's Q1. Here's, sorry, my cat came out. This is at 2a, so it'll be 2a plus 1a, which is 3a. W. But we can simplify this more, right? So if we take it as we multiply 3 against e and then negative 2 against e2, then we get 1 over 4 pi epsilon naught. And this is negative, of course. I apologize for that again. I forgot. I took out the negative when I had the negative e. And then that'll be e squared over 6a. Right? Since it's 3 e squared minus 2e squared, which will just equal e squared. Right? And then we can combine that together to be negative e squared over 24, since 6 times 4, pi epsilon constant a. Hey there, Hito. Sorry, I just got a new kitten recently. Very loving. Needs attention constantly. Okay, and that was for problem E. For problem F, right? It asks us to find the potential energy of the system with 3 charges. It may seem more complex. It's not that much more complex. But this time we got to remember, we got to measure all of it, not just 2 particles affecting 1 particle. We need to find the full potential energy of all 3 particles, right? So to do that, we will set up the problem as negative 1 over 4 pi. Draw out that negative sign again, times epsilon constant, times e squared divided by 2a, since that's the distance, 0, plus a squared over a plus e over 3a. Sorry, this should be negative. Okay, and for this, we can just multiply again. 2 times 3, so this will be 6e squared. I heat though. 6a plus, I apologize, that's 3e squared. I actually took this problem because I struggled so much with these originally. But now, after a few times of practice, I've got a pretty good concept of it. 6e squared over 6a plus 2e squared over 6a. What we got to remember is that since this is negative on this bottom part, these will also be negative. All right. Sorry, I'm doing mental math while my cat is jumping on top of me right now. And hard to focus. But then we can simplify this down to negative 7 e squared divided by 24 pi epsilon naught a. Right. We'll make sure to write down joules for that as well, and joules for this one. Just make sure we keep all of our labels correctly. All right, and on to part G and H. For G and H, they want a point charge Q1 equals 5 nanocoulombs is at a fixed position, x equals 0, y equals 0, and z equals 0. You find that you must do 8.10 times 10 to the negative 6 joules of work to bring a second point charge from infinity to positive 4 centimeters on the x-axis. What is the value of the second charge? Okay, so let's write down our values first. Q1 equals 5 nanocoulombs. And it is at x, y, and 0 as a vector. That equals 0, right? And there's a second charge, Q2, that is unknown. That's what we'll be looking for in G. And we bring it to x. Sorry. Got a little bit more technical than I needed to be. X equals 4 centimeters. And we need to use our work done is 8.10 times 10 to the negative 6 joules. All right, does this look familiar to you guys? It should. This is pretty much just the exact same equation. Sorry, my cat is stabbing my leg. I apologize for that. Oh, that one hurt. Okay, so for G, we'll just have to use the exact same equation that we did before. I believe it was. Damn this. Yes, where we reset it. So we'll pull exactly from there. Use, since we have the distance, we have Q1, we have the work done, and we have K, since that's a constant, we just need to use U times R divided by Q1 times K, and that will equal Q2. Okay, so we can work on that. We'll just plug that into a calculator real fast. 8.1 times 10 to the negative 6 times the distance of 0.04 meters times Q1, which is 5 times 10 to the negative 9 coulombs times K, which is 8.99 times 10 to the 9. So, I apologize. Let me rewrite that out again, just so we can all be on the same page of what I'm doing, so we can make sure my values are correct. 8 times 10 to, or 8.2, or 8.1 times 10 to the negative 6 times 0.04 centimeters. 0.04 meters, I should say. My cat's very curious recently. I am so sorry for that. Tito, you gotta stop. Okay. For Q1, it's 5 times 10 to the negative 9 times 8.99. Sorry about that. Times 10 to the 9th. And that will equal 7.21 times 10 to the negative 9. Give me 1 second. Let me deal with my cat real fast. I am so sorry about that. Okay. I ended it before I could label this unit as joules for work. Or I'm so sorry, not joules. These are coulombs. It's important to remember what we're trying to find. These are the coulombs for that atom, or for that charge, I should say. Okay, and now it's asking us once the second charge is in place, so once it's all where it's supposed to be, you bring a third charge in that is 2 nanocoulombs to the position of y equals 3 centimeters. Okay, so a little bit different. We're bringing in a whole different factor. So let's remember one charge is here, one charge is here, and we bring a third charge right about here. And we want to know how much work is done to do that. Okay, so we'll just go back to our work equation, right? So we'll apply y equals uh, k times that third particle, right? So 2 nanocoulombs, so 2 times 10 to the negative. Or first, I'll just write out the equation so we can all understand. So you guys can apply it too if you need to. Times Q3 times, let's use the one that we just found, 7.21 times 10 to the negative 9 coulombs. And now let's remember, this is not directly, it's not just straight up 3 or to the left 3, right? It's up in 3 and then to the left of 2. So we can use Pythagoras theorem for that, right? Just figure out the magnitude of that vector. That'd be, so let's remember, a squared equal, or plus b squared equals c squared, right? So we have a and b, so we'll need to take the square root of the magnitudes of each. So that would be 9 plus 4 equals c, 13, square root of 13. But it's also very important, I almost forgot about this, to remember that 0.03 squared plus 0.04, or 2 squared. Okay, so we'll plug that into our calculator. Take the square root of 0.03 squared plus 0.02 squared. And I am so sorry. It is not 0.02 squared. It's 0.04 squared. 0.03. So then we will get 0.05. Okay. Plus 5 times 10 and negative 9, negative 0.03. We don't really need negative there, but yeah. And then we can multiply that out. And when we do, we will get 5.59 times 10 to the negative 6 joules. And that is how much work it takes to bring it down. All right, all very basic problems, but thank you for watching. All right, bye.